start with English. So this good afternoon. It's my great honor to join today for this conference. Not only that serve as the College of Dean, I'm also the chairman of the IEEE Catholic section. So I see my IEEE member here. So I'm very happy that you come to this this workshop. So I think this is an international conference. I'm fuzzy. It's a very important global humanity, intelligence, communication, fuzzy logic from many applications such as manufacturing, healthcare, and really to teach us how to take advantage of this ambiguity to find a priority, and also find from a complex system to find your intelligence. So, so this is a very important area. So I like to extend my heartfelt appreciation this to the organization, committee, and people, authors, and reviewers, and also all the participants come to the our college to participate this event. So I wish you all have a success conference and the memorable stay in Taiwan, especially in Hsinchu, Jiaotong. Thank you very much. 换成中文讲这样，谢谢这边有像我们很惊讶的跟讲座教授哈，跟教授的好朋友回来我们交大就这样的那iPad 这个是一个智慧运算模糊逻辑那我想这个在我们现在人工智慧很红之前，我们就在做这些在发展的这个领域中那在模糊中找到信息在复杂中找到智慧。那我觉得这是非常好的一个研究领域那我们今天很高兴大家再重新回到交大这边来探讨我们这样的一个主轴那谢谢大会的这个主办单位跟教授还有很多的同仁努力举办这个活动谢谢大家努力在这个学术领域在跟我们的帮忙跟我们指导祝大会成功这个新竹交大在台湾收获支持大家这个拥有美好的回忆，谢谢大家。
Okay, thank you, Ding Wang. So then I will invite Professor Chun-Soo Wei to share the keynote talk.
Okay, good afternoon, everyone. I'm Chun-Soo Wei. So next we will have a keynote speech diving into a frontier of brain-computer interface and augmented reality in the metaverse. So our speaker, distinguished Professor Jingden Lin, he has so many achievements, so I have to put it on my phone. So from University of Technology Sydney, he's also the director of UTS Human-Centric AI Center, co-director of the Australian AI Institute, and director of the CIPCI Lab. So he previously served as the international faculty at UC San Diego and as an honorary professor at the University of Nottingham. Professor Lin is a leading figure in computational intelligence system and human-machine interactions. With more than 460 journal papers and an H-index of 98, he authors books of neural-fuzzy systems and served as editor-in-chief of IEEE Transaction on Fuzzy System and sit on multiple IEEE boards. He is an IEEE Fellow, recipient of IEEE Fuzzy Pioneer Award and the UTS Chancellor's Medal of Research Excellence. So personally, I joined Professor Lin's lab when I was a freshman here in 2005, and later I completed my master's degree with him in 2011. His inspiring mentorship has not only profoundly benefited my career, but also for many other scholars here. So today he will show how BCI can augment human performance and daily care, and what these advances means for the coming metaverse. So now please join me in welcoming Professor Jingden Lin.
Good afternoon, ladies and gentlemen. It's my great pleasure to stand here again to present our recent research on brain-computer interface. Actually, I remember last time I stand here is I gave the last lecture on fuzzy logic in 2015, so almost 10 years ago. So yeah, so it's very impressed I can be here again and really appreciate for your time. So the topic I want to present to you today is BCI brain-computer interface in augmented reality and metaverse. Actually, I will more focus on the some new brain BCI technologies. But I consider one potential good application is in the metaverse. Okay, I will introduce you to you. So the outline that including I will introduce the BCI first, and I will talk about the BCI in metaverse application. Then I will present two main research topics that I'm working on in the past 10 years. Actually, more than 10 years. Okay, and one is SR, VR AR based BCI, and second is a more challenging one is EEG to text. That is to decode the brain signals when people is imagine speaking and into the words. Okay. So BCI, BCI is to extend the capacity of brain in communicating and interacting directly with things. So there are two major kinds of the BCIs. One is active, one is passive. Active BCI is to detect the voluntary control in people's brain. For example, use the BCI to control the wheelchair or to control the robot remote. So this is active BCI. The second is the passive BCI. The main function is for cognition assessment, for example, for fatigue detection in driving. So there are two key technologies for BCI. I should emphasize here, BCI in wide sense, in a wider sense, including invasive, non-invasive. But my research is more focused on the non-invasive. So I mean, it's kind of the wearable devices. So there are two main technologies. One is hardware, one is software. Hardware means that we need the wearable EEG headset. Important component is the stride sensors, just that people can wear it freely, and also the other circuit. The other part, more important, is AI algorithms to decode what's going on in the brain. And so I will comment a little bit about the devices first, and then I will part. So I forgot to appreciate Li first to invite me to here. And actually, this is the joint work me with Leo and many other people here. And so, so it's a wireless. We focus on mobile and wireless EEG. So this is the picture. The photo shows the traditional or the standard setup for people to measure the EEG signals in medical, in hospitals or in research lab. So you can see a bunch of wire, and more importantly, the sensor that we use is that we call it a weight sensor. Means that we need to apply the conductive gel to the sensor to keep the good conductivity between the metal plate and the scar surface. So this, of course, this can get a very high quality EEG signals, but not good for the daily life applications. So actually, this is what with this kind of the EEG headset was developed here with Professor Gore and many other my team members here. And so it's become a wearable devices, wearable head. There are two, so to develop just kind of the wearable EEG headsets, there are three key components. The first one is dry sensor. Let's say we don't want to use a conductive chair, so in that case we need something dry. So it's kind of a dry sensor. So in the past more than 20 years, we developed a series of the dry sensors. So I don't want to go through the detail, but basically there are two kinds. One is multi-finger type, one is flat. So the flat type is good for the hairy side, for example, the horset, the forehead. And the multi-finger type is for the hairy side, because we need this kind of design, mechanical design, to penetrate the hair that it can touch to the scalp surface. So there are two major kind of design. And the other dimension is the material. What kind of material? The most basic one is metal, silver metal. The conductivity is very good, but it's not so comfortable. Also kind of heavy. So the other is more flexible type. It's a kind of the plastic. The diopressive is a conductive by coating some different kind of the material. So this is the dry sensor. We need a dry sensor. And the second key component for wearable EEG devices is the amplifier circuit. I think this is, you can understand this. And so, for example, we could also make it to a chip, VCI chip. I cooperate with the Taiwan National Semiconductor Center in the past six years, and then we designed this chip. I take out earlier and to SMC and improve in work. That's work quite well. So this including this chip including the amplifier and also including the deep learning model, deep learning model embedded. Okay, so this is the hardware. The second, we need a circuit or even an IC. And the third part, something like this. Okay, so actually the third part is the form factor design. Sorry, so just that kind of form factor design. Just that can house the sensor and also can fit various kind of head. The headset is very complex for different people. Okay, so this is one application in, as I say, integrated sensor in the HORS or in the VR glasses or AR glasses. So when people wear the VR glasses, then it's naturally the sensor can touch to some part of your head, depends on your applications. Okay. And of course, right now the devices are quite available commercially. Several companies already produce this, so it's easier to buy it. Okay, so this is hardware. Okay, and I touch a little bit. So I finished the hardware, and then it's a software. Software is AI part. So I'm one of my main topics that I want to introduce to you is a silent speech. But also the first topic also related to some technology here. So I use this slide to introduce some way that the VCI technology can understand the human intention and then pass through the machine. The first is there's several. One is passive VCI. The most famous one is we call it SSVP. It means that we present the flickering on the screen or on the VR display and to the human, and then we detect the brain to understand which flickering. Different flickering have a different frequency, different frequency. So we can understand from the brain signal which flicker the subject looking at and corresponding to different kind of the command. So this is the passive VCI. But the disadvantage for the first one is that it's a stimulus phase. So we need to provide a stimulus to the human and then to see the results of the brain. So this is good. But in some application, it's okay, but in other application might not be so suitable since we need to provide an external stimulus. And the second method is more imaginary. That we think we don't need external stimuli, but just think about the left hand move, right hand move, or her body move, or finger move, and then we can detect from the brain signal which kind of movement that you are thinking about. For example, you think about if you think about the left hand move, then I can understand how it's left hand move. Then we can define a command. For example, as a robot to turn left or turn right. So this is a motor manipulation. The good advantage is that there is no stimulus, external stimulus needed. But the disadvantage is that there are quite limited commands. For example, right now, 3 commands, up to most 4 commands. The accuracy could attain 70% or 80%. With more than 4 commands, then the accuracy drop. It's not easy to get higher accuracy of this. And the third one is what I want to I focus on. In the recent years is the silent speech. It's very challenging, but the advantage is very natural. But exactly like what I'm talking to you now. Talking about so the task is that we ask you can speak. You don't need to speak out. You speak out in speech recognition technology to help. So don't unspoken language. When you unspoken, but you speak in your brain, and we can detect the brain signals and detect the words that you use, and then use the large language model to translate into a text or into a sentence. So I will introduce this data. So it's more natural, and more challenging. Okay. So this is VCI. The second is VCI in metaverse. So metaverse. Actually, today we have real world, and we have in the real world and metaverse, and so they must have a way to access the real world and the metaverse. So I'm thinking that VCI is a good technology to connect these 2 worlds, the physical world and the virtual world. And especially talking about the human in the real world. And we also have virtual human in the metaverse, in the virtual world. Then how to make the human in the virtual human in the virtual world quite close. We cannot say exactly the same, but quite close to the real human. And so the VCI technology could help, since VCI technology can understand more about the human, the cognition way, and then so in the virtual world, that we could understand other persons, what the cognition status of the persons. So in other words, we can create the kind of the human digital twin of the same people in the real world, and also the digital twin of the real human in the virtual world. And they could share some similar brain status or cognition status. So that is my thinking. So for example, that in the real world we have various kind of the sensors, wearable sensors, including the EEG sensors, and then we can measure the status of physical human status in general. And then so in the digital twins, we can also have just kind of the understanding. So SDT, a human digital twin. So for example, in emotion, then we can simulate or animate the stress, calm, label, and cognition, workload, or fatigue, and thoughts, imagine speech, or body movement, pose, or muscle. Okay, so this is the general idea that I'm consider that the VCI is a good tool for people to create a human digital model in the metaverse, in virtual world. Okay, so today's talk is more about the ATVCI. It means that how to understand the human intention and also in the virtual world. So as I said that there are several technologies I just mentioned, P300 or MI or SSVP, and today I will more focus on. So this is current technology. I'm talking about the visual technologies, the imaging, speech, decoding. Okay. So then I will introduce 2 main research topics to you. one is the SR based BCI. So this is the HORIX, and so this is a pad, the sensor pad that we developed in the day, and so this is the sensor, and so so this is a device. So when people wear the system, then we can also measure the brain signals simultaneously, and to do something. And this is a so the first topic is about the SSVP, a quite traditional VCI technology. So we're looking for the more real-life application of this technology. So I introduced. So SSVP is a brain response to repetitive visual stimulation at specific frequency. I think that I just explained to you later on. There are different flickers, and they were flickering at different frequency, and so the general method, the quite famous method to decode this is a CCA or TRCA. I think I don't need to go to the detail here. And so basically, I think it's easy to understand when people look at, for example, we put people look at the flickering at the 10 Hertz, then I can detect from the brain signal, especially on the on the visual cortex area, and then we can detect, and our algorithm can detect, oh, it's a 10 Hertz, then I know which flicker he's looking at. And so, but the problem here is that when the number of flickers increase, then it will become confused, and the accuracy, the recognition accuracy will drop. So what we propose here is the 3D SSVP. So traditional is the 2D flickering, and then we extend it to another dimension. This is rotation, so become a 3D flickering. Become a 3D flickering. Yeah. So the 3D flickering. So in addition to the different frequency, then they will rotate a rotation. So in other words, our decoder will decode not only the frequency but also the flicker. So for example, option 1 is 7 Hertz but rotate that. So another dimension. So this can increase the accuracy, or also can increase the number of the flicker that you can display at the same time. I think the number of flicker corresponding to number of commands, right? The number of commands that the user can issue. Okay. I think just a little bit. For example, we just use a simple CNN, and we can, since when the flickering rotate left or rotate right, and from the brain head, the heat map, then it's very obvious. Is the occipital area, we can see that is either the left hand side or left hemisphere or right hemisphere occipital area will light up. So this is another simple dimension, but I can enhance the accuracy and also a number of the flickers. So this is the 3D. So this is the video that we show in the lab. So you can see there are 12 flickers, and each one is flickering at a different frequency, and also they will rotate. One rotate to left or rotate to right. So when we detect, then we can combine this detection. We detect the frequency, how much, what's the frequency, and how's the rotation direction. Get better accuracy. So, and also I use this technology in a project in Australia with Australia Defense about 3 years ago. It's not new, but not new. But since this is a defense project, so we have some new result, but we have to wait until they announce, then I can present to you. But they announced one video about 3 years ago. So I can show you here. Some of you have saw it, but I want to show it again. Okay, and this is some experiment in my lab. Okay, I will show this. This is a newest one, but non-defense related. Okay, so I'll show you how apply this for the remote control, the multi-robot. Let me explain this a little bit before I show the whole video. So you can see the screen here. The screen here. This is a screen that see by this is my is yours where the whole is. So you can see the display on the AR glasses. So you can see there is a button. So you can select one action from here. This is one part. This is artificial command panel. And the other is that you can set the location, the waypoint, target location in the space. And so this is also has speaker on it. So this is, for example, you can set the mobile vehicle or the drone to fly to the side, the second side or the big side, which are in the air. So in other words, you will see the figure two part. One is the figure in the air that is corresponding to the physical object in the space, such as the user can select it as a destination or the waypoint for the mobile robot, or for the drone to reach. The other is a kind of virtual panel, command panel. Then you can select some command. For example, move forward, move backward, or stop. So this kind of two kinds. So you can see since this is AR basis, so we can design that kind of control panel in a very flexible way. Depends on your need. So this demo is for to control two vehicles together. One is drone, one is the mobile robot. So.
I will activate the drone. Activate. I will switch robot drone. Okay. Drone position 1. Nice. Drone position 2. Nice. Drone to position 4.
It's an intruder.
He'll come to me. Yep. And I'll switch back to Jekyll. Nice. Double control? Huh? Double control? Yeah, double control.
So you can also see the this is image
When,
from the mobile robot or from the drone. So outside of the human's side of view.
So, I'll switch back to drone again. The wind is windy, really windy. I'll deactivate. Activate? Wait, okay, deactivate. Nice.
Okay, so you can see there's a small image window. This is through the camera on both mounted on the drone or mounted on the mobile robot. So in other words, even the mobile vehicle or the drone is out of our the side view, and we cannot see it by our own eyes. then we still can give a command, use this technology to it based on the image that's streaming back to the graphics. So it's so it means that it can control the drone in quite long distance. When we can get an image of the drone back to display on my graphics. So this is the new technology that we developed on this. Actually, we will have a field demo test the kind of the final deliver in next 2 weeks in Adelaide in the field. But this is on the campus. So I just show you first. And the next slide is the kind of the field, the same field test, but performed 3 years ago. It's more formal.
Today we conducted a successful demonstration with the University of Technology in Sydney, consisting of 4-way collaboration supported through the Defence Innovation Hub and using our partnership with Defence Science and Technology Group, DSTG. This 4-way collaboration focused on how we could create a brain robotic interface that will allow a soldier, rather than operating an autonomous system with a command console, to operate the system using brain signals. What was created was a headset that a soldier could use using a HoloLens 2 model that had an AI decoder via a Raspberry Pi that would translate brain signals into explainable instructions. What's so exciting about this technology is it has the opportunity to use with a number of different autonomous systems. We conducted 2 short demonstrations today. The first demonstration showed a soldier operator commanding an autonomous system, being the Vision 60 Ghost robot, to a series of waypoints along the ground, and this was conducted successfully.
The potential of project is actually very broad. At its core, it's translating brainwaves into zeros and ones, and that can be implemented into a number of different systems. It happens that in this particular instance, we're translating into control for a robot.
The second demonstration was having a soldier operator acting in the role of a section commander and providing directions to both the Ghost robots and other members of their fire team. And they conducted a simulated control clearance of a number of buildings here at the Madeira Range Urban Operations Centre.
This technology enables me to not only control the Ghost robot as well as monitor its video feed, but it allows me to be situationally aware of my surroundings as well as my team to be able to control all movements of that battlefield clearance.
This is very much an idea about what might be possible in the future. We're really excited to see where the technology might go and to work with our stakeholders to develop a wider range of use cases in order to better determine how we can support the military practitioner and the warfighter.
Okay. Yeah, to save time and go to the next topic. Actually, this is the main course. And what I present to you is just the entry. So this is a short course. This is the main course. The BCI-based EEG to test translation. The idea actually can trace back long in 100 years ago. There is a paper at the New York Globe. The title is the test photo of human thought, published in August 1911. Okay, the first year of the ROC, Republic of China. Okay, so this this title of this newspaper. This is the by a researcher called Target in Paris. Okay, and I just extract some main cross here. In red is the New York Globe on August 16, 1911, in an article entitled "It's a photo, a test photos of human thought." There's a commander His name is Target Paris, who claim to have captured photographic image of the human thoughts using obscure V-rays and intense mental focus. But that's what is claimed. I have no good idea what he really see on this, but he claimed they use V-rays. I also have no idea about V-rays. I know about X-ray, but I don't know what's the V-rays. But anyway, this research you can trace back more than 100 years ago, and so about so the brain to text or EEG to text, the human communicate and interact through their thought. Can decode the brain signal when people is speaking in the brain and make it into the sentences. For the application, there are two kinds. One is for the people with hands-free silence communication, such as when silence communication are required, for example, when privacy or required or with noisy background. Or more importantly, this technology can benefit the people who are unable to speak due to the stroke or paralysis. Okay, so what we develop now, we call it the large brain language model, LBLM, large brain language model. So it can decode the brain signal into the words and then composed by sentence by the large language model. And where I am focused on the EEG is more challenging. But actually, they already have some good result from other modality. For example, invasive BCI for brain to text, ECOG to text. Also, there's a research published 2021, still quite new, in Nature paper. And what it did is that put the needle into the brain, and then it track then detect the brain signal inside the brain. So we call such kind of signal, we call it the ECOG signal, and then it's a phony based decoder and decode by the user N-gram language model. So it is the ECOG to phony to words recognition. The accuracy is quite high. It's up to 90%. It's quite high. But people have to open the brain and put the needle in the brain. And so this is invasive. And non-invasive, also quite new, in 2023 or most paper 2023, published in Nature Neuroscience and Nature Communication. They use the fMRI. So still, it's non-invasive, but still a very heavy machine. But this study is about hearing instead of speak hearing. It just speak the sentences and for the subject to hear, and then at the same time to record the brain signal, fMRI signal, and then decode from the fMRI signal to decode it to see what the words or what the sentences that he heard or he or she heard. Okay, so this is the reason. Okay, so my goal is more ambitious. It's EEG to text. This is a very basic function. After filtering, when we got the EEG data after filtering, and then we had to perform the noise removal, and then we check the biomarker, and through the deep learning, we to understand the words, and then from the words, and then we have a set of words, and with different probability, and then decode the words into sentences through the large language model. Okay, so this is quite a basic concept. So actually, we have developed a series of the backbone for this is, as I told earlier, is the large brain language model. We just put the brain in the LLM, so LBLM. Okay, large brain language model. Actually, this name is invented by Professor Zheng Mingyang during our discussion. So large brain language model. And so we have developed a series of the model since the 2023, different model, Bear model, Beware model, and up to now. And so due to time limit, I cannot explain all the model. Actually, here the most famous one is the Beware model. Since this one was published in the NIST conference, very top conference in AI, and also this has been selected as a highlighted paper. And also this paper, the ACM, and then it just held. This conference just held last week in UK or UK. I was not there, but my PhD student was there to present this model. So just give you a feeling about the Dutch brain language model. I just want to focus. Okay, this platform is messy. Okay, so majorly the platform including two part. One is including two part. One is platform. One is classify. So platform is to decode the words corresponding to the EEG signal and then identify the word. Also platform. It's a raw signal, and then platform will produce the kind of the internal representation. In AI, we call it the latent representation, and then we use a classifier to classify words. And so this is about the, I think this is a large language model. So this is the EEG data. We patch it into segment by segment, and then we apply the conformer here. Of course, we have different kind of we can apply different kind of structure. But basically we use a conformer. Conformer is nothing but the very famous transformer. We embedded the convolution module. So this is a transformer, a standard transformer architecture, and we embedded. Now we actually also quite famous conformer, a convolution module. And one important feature of the transformer is self-attention, multi-head self-attention. Okay. So just for your references, I will talk about this a little bit later. And for the spatial temporal classifier, and this is just a multi-layer classifier for the classification purpose. Okay, so this is, I want to mention a little bit about this model, large brain language model. So basically we have the EEG, we had the EEG encoder, and then a large language model decoder. And so normally when we train the large brain language model, we rely on a huge volume of the data, the label data. I think label is important, always troublesome things. So this technology that is considered that we make use of the unlabeled EEG data to enhance the training, and then we can fine-tune the model based on the label data. So this is concept. So just that we don't need a huge number of the EEG data. That need to be labeled. Okay. So there are two stages here. So it says supervised pre-train first, and then go to a supervised fine-tuning, and how to self-supervise. So our major goal in training, one is we construct some missing EEG data. The other is to predict some unseen forecasting some EEG data. So we train the model in this way, just that the model can learn the more representation power of the EEG data. Okay. So I think this is some detail about this. But basically, in the self-supervised training, we try to mask the no EEG data and it's a patch different segment of EEG data, and we purposely just mark some segment EEG data segment, and we train the platform to reconstruct this or to predict this missing part. Okay, so we don't need a label. We just reuse the EEG data. This is so-called self-supervised training. So after the self-supervised training, we still rely on the label data for the fine-tuning. Okay, so this is the key point for this model. So for example, let's just show you some results. So the large brain language model prediction capability, it's just based on this and to predict this, and this is ground truth. So it quite matched quite well with the ground truth. Also for this one, and this for prediction, and this is for reconstruction. So for example, this part of the segment is missing, and then you can reconstruct and you quite fit the original data quite well. So we use this we so-called the self-supervised learning to enhance the representation power of the large brain language model, and that we can see the enhance of the accuracy. So we don't need a lot of data, a lot of label data. Okay, sorry. Okay, the other thing I want to present to you is more important. See, this is a fuzzy conference, right? I have not touched any fuzzy. Okay, so the other important thing for any VCI application is transfer learning. So I learned transfer learning from Professor Chu Wei, and also my students learned from him. And transfer learning. So here we for this conference is iFuzzy 2020. So we propose a model called iFuzzy TL. So just for this conference purpose. So iFuzzy TL. Actually, just a coincidence. My student named this. I asked him what does I mean. He said I means the interpretable. Okay, so for iFuzzy, what's the meaning? Okay. Okay, so cross subject means that when the model fit well for one subject might not fit well for the other, since due to the subject relation, different people have the like relation among other people. And so the transfer learning, what we should propose is that we have a set of subject here, and when there's a subject, we will see we have to get some data from this subject, and then we will check out which group of the existing subject most fit this new subject, and we can use the model there, or we can fine tune. So we call it this kind of few-shot classification. So what we want to propose, the fuzzy here is a zero-shot. Zero-shot means that, okay, for the new subject, we don't need to get any data from it, then we can, it's very magic, right? Again, we don't need to get any new data from it, but we can ensure, we can select some model here. I can ensure the higher accuracy of this new subject. So this is a zero shot. Now how to do that? Actually, we use the fuzzy. So this is attention network in the transformer. Attention transformer is very powerful, right? So as a ChatGPT, but one key component for it is set attention network. So this is the standard set attention network. So the three components VKQ. Q represent what each element is trying to find, and K is represent what kind of the information each element is over, and V is represented the actual context. I use Apple as example. So Q is that please tell me what kind of group, what group has red color and hot more field. Okay, and this is Q. And the P is kind of knowledge. So the transformer has a global dictionary that including all knowledge of the group. Okay, that's the key. And value is that after searching, compute attention with the best matching content is able. So this is the way the attention network is working. And so attention width. Okay, so we can see that we can transfer it into the fuzzy logic. So this, as I said, this is a standard attention network, and we propose the fuzzy attention network. So Q is a relation of each fuzzy word, and K is the parameters of the fuzzy memory function, and V is the fuzzy consequence representing the actual context corresponding to the fuzzy word and observation. But I think it's easy to understand is that I think all you understand the fuzzy word is if A then B, right? If input is A prime, then what is output B prime. So corresponding here is the Q is A prime. So Q is A prime, it's observation or the input, and K is knowledge, so it's A, and V is a consequence. So this is a precondition, and this is consequence. So we construct attention network into a fuzzy attention network in this way. Okay. So this is the basic component of the iFuzzy TL. Okay. Okay, I think. Sorry. Oh, it's a more complex, but I just described it. So, okay, so this is a load signal, and then this is a target subject is the current subject that we want. We get the EEG data for us to do analysis. And so, here we design two partial attention network. And so this is a VQK. VQK corresponding to if A then B and then A prime the input, and then to calculate the value trends and get output. So this is you can consider this is kind of fuzzy filter. Fuzzy filter, and this is also another fuzzy filter. But we design two. Is that this one is for spatial fuzzy filter, and this one is to the temporal spatial filter. So in common in plain text is that this is low EG data, and after this, then we can filter out or focus on the data. They are important to the output, to the final outcome on the spatial domain. And then we go for the second filter, fuzzy filter, and further focus, further filter out the important information on the temporal domain. Okay, so this is a general concept for this one. So it's a two layer of the attention. But we use a fuzzy inference for this process. Okay, so the advantage, there are advantages. For example, completion, the visual variability, resilience, detect decision making, and fewer filter. I think all these 2 points is just use just being mentioned as the fuzzy. Whenever we talk about the advantage fuzzy that can address the uncertainty issue or the randomness issue. So these two are the advantage. And the third one, pure filter, that's our specific design. So we can learn where and when the relevance neural activity emerges by a pure fuzzy attention filter. And the last one is dual specific knowledge representation. I think up to this point, you might concern and what's that related to the zero shot? What's that related to transfer learning? Do you know? Actually, so this is the last point. Dual specific knowledge representation. Sorry, is seen as set of observation in a different rule. So that's a very important advantage of fuzzy logic in the rule base. So you can consider each rule or different group of rule are some kind of classic, the concept classic. So could represent the characteristic of a specific group of people. So it's kind of, so when we get the input, then we'll find the related rule. That means that it implicitly will clustering this new subject to the right cluster, and then to do the right decision making. Does that make sense? so it's kind of the we call it the implicitly, not implicitly transfer learning already embedded. Since fuzzy rule is a with clustering, right? So it's a kind of localization effect already there. And for each cluster corresponding to a different group of people with a similar features. Okay, so when we got the raw data and the system will find out the right words to find. So this is a kind of the transfer learning implicitly. Okay, I hope. Okay, I think I run out of time now. Okay, so this just shows some result of the silent speech. I mean, maybe I show this one. Okay, so this is a one experiment. And so the user select a sentence calculate one missing words, and so he will speak silently, and then our system will recognize word and to finish the sentence. So you use the SSVP to select one sentence you want to say, but the keyword is missing. In keyword design, that depends on what you want, what you like.
Running.
Okay. So I stop here. So if you hear the sound, it doesn't mean that we recognize the sound, since we had to have the ground truth. So the people beside him will tell him a word, and then he will speak the word in the brain, and then the system recognize and to finish the sentences. And so this is a whole sentence. So you speak the whole sentence, word by word. So you can see this word with different probability, and then the large language model will decode the final sentence. So this is another example. Okay, sorry. I just want to show. So this is output the last brand language model. So for this word, actually, there are some candidate words, but with different probabilities. So all information on the last language model can be used to synthesize the final sentences. Okay, and so I was invited to give a TED AI in Vienna last October, and I give a talk here, and there's a link, so you can check it on YouTube, either YouTube or the tech website by itself, and mind reading. For example, using mind reading, and you can check it out. And so before the talk, I met some of my former students, and then he said that he can help me to have people to create a more clip on it. So there's the Dean of Academic Affairs. So this is the link. This is the link. And if I have a website link, I might. Took some time. Oh. Time's up, right? I know. So finish. I just want to enhance the number, a digit number. Right now it's a little bit low, just 377 times. But anyway, okay, I skip it. Yeah, we can just search it and with my reading and AI. Okay, so I also got an interview, the ABC interview, Australia Broadcast Company this June, and I will use this as the ending of my presentation.
What if you could operate your mobile phone just by thinking about it? Bridging the gap between computers and the brain is the latest scientific frontier. Researchers at Sydney's University of Technology are experimenting with ways to use artificial intelligence to read your mind. Turning thoughts into text on screen. The cap Daniel is wearing is recording the rhythmic patterns of his brainwaves. As he reads the sentence, Daniel mouths the words, which enhances the way the brain recognizes speech. An artificial intelligence decoder then translates his thoughts into words. It's close, but not perfect. To prove this isn't a trick, I must choose the word Daniel should think of to end this sentence. Spoon. The AI reader gets it right about 75% of the time. The team is aiming for 90% accuracy. The technology uses two types of AI to decode the brainwaves.
At first, we use a deep learning model to translate the brain signals into the intended words. And then we use the large language model to make a match of the decoded words and make up for errors in the EEG decoding.
Unlike earlier models, this technology does not need to be implanted in the brain. Experts say it could be used for rehabilitating stroke patients.
As scientists, we look at a medical condition and we look at what function has been affected by that medical condition. What is the need in the patient? We then address that unmet need through technology to restore the function back to what it was. After that, decisiveness.
A wearable device that can read your mind used to be science fiction. Now it's a step closer to reality. Technology that allows us to perform tasks just by thinking about them. And could one day even be used to read each other's minds. Catherine Herman, ABC News, Sydney.
Okay, thank you.
Thank you, Professor Jenny, for your inspiring talk. So I think due to the time constraint, we can ask one question.
Okay, considering that's wonderful speech, very inspiring and forward-looking. My question is, if a mother wants to use the technology, she cannot speak English. So can your system work to Taiwan?
Yeah. Thank you. Then, yeah, I was asked this question many times, and so right now we focus on the English. So if we want to, the system can work on the other language, especially Mandarin or Minanhua. And of course, we need the we train the model, we need the data, we train the model. So unfortunately, we need to do so. But the good part is that, as I said, the large brand language model is so powerful. So actually, we train the large brand language model not only on English, we create all the data in Word, including the not English words and help. Actually, in the beginning, we even train the model, pre-train the model by the speech signal. This speech signal is quite similar to the brain signal. So what I want to say that the large brand language model already has some potential to fit into different kind of language, but still have to retrain it. But the retrain will be the time consuming and effort will be much less than we train the empathy model from the beginning.
Thank you.
Thank you.
Again, let's thank Professor Jin Teng.
Thank you.
Okay, we organizing committee also prepare a gift, souvenir, and also the appreciation to Professor Lin. So I would like to invite our NSPC convener, Professor Zhuang, and also General Chair, Professor Zhong, to give this the appreciation and the gift. Okay, let's thanks again to Professor Lee.